In Form 2 on the chapter on magnetic effect of an electric current, we observed that a current carrying conductor generates a magnetic field around it. This discovery by Hans Oersted in 1820 opened a whole new vista for research, and what many wondered is whether the converse can be true. Could a magnetic field induce current in a conductor? And it wasn't long, as one can imagine, before new discoveries were made. In 1831, Michael Faraday in London and John Henry in New York independently discovered that indeed the converse was true. A changing magnetic field can, under special conditions, induce current in a conductor. This is called electromagnetic induction, a phenomenal discovery that ultimately led to the birth of electricity. Let us see electromagnetic induction in a straight conductor. What we have is a conductor between two arms of a horseshoe magnet. The two ends of the conductor are connected to a galvanometer by means of wires. When the conductor is moved downwards, the galvanometer deflects, indicating that a current is induced in the straight wire. When moved upwards, the galvanometer is deflected momentarily in the opposite direction, indicating that current is flowing now in the opposite direction. If moved parallel to the magnetic field, the galvanometer shows no deflection, indicating that no current is induced. When held stationary in the magnetic field, the galvanometer again indicates that no current is produced. We can also induce current in a circular coil of copper wire. We connect its two ends to the two terminals of a sensitive galvanometer with the scale indicating 0. Note that this circuit has no source of electricity. We take a bar magnet and move it swiftly towards the coil with the north pole facing the coil. We observe a deflection in the galvanometer when the magnet is moving, indicating that current is set up in the coil. Move the magnet away from the coil. The galvanometer deflects, but in the opposite direction, meaning that current is set up in the opposite direction. If you move the magnet with the south pole facing the coil and repeat the steps, the deflections occur but are reversed. What if the magnet is held stationary? No deflection. This is very important, that current is only induced if there is relative motion of the coil and magnet. Only when the magnet is moving is there deflection. But when it stops, the galvanometer pointer comes back to 0. The current produced by the relative motion of the coil and magnet is called an induced current and is set up by an induced EMF. The production of an induced EMF in a conductor in a closed circuit by the relative motion of a magnet and a conductor is called electromagnetic induction.